So we'll continue, excuse me, we'll continue our investigation of different integration techniques. We looked previously at integration by parts, and then integrals involving trig functions, in particular products involving sines and cosines, powers of sines and cosines, and then products of powers of tangent and secant, among other types of trig integrals. Today we're going to look at something known as trigonometric substitution, which actually doesn't start with an integral involving trig functions, but introduces trig functions in way of a substitution. So this is a little different than our standard substitution technique. Our integrals will generally involve forms that look like this, and so here a is a constant that is positive, x is the variable, and you can see I have the square root of a squared minus x squared, the square root of x squared plus a squared, and the square root of x squared minus a squared. Of course, you see the difference, the subtraction matters, right? The order we subtract in. So x squared plus a squared would be the same as a squared plus x squared. Now they're all under this radical, but we'll also look at forms that are essentially powers of this radical. So we're basically looking for these forms where we have these three forms, and having a radical involved in the integrand makes things rather difficult to try and evaluate and find the antiderivative. But we're going to look at this technique using an introduction of trig functions, and I want to remind you of our three Pythagorean identities. The first two in particular will come into play in what we're going to do here today. So let's take a look at this first one. You can see it's an integral involving a squared minus x squared. It's this first form where a would be equal to 1 in this particular case. And what I'm going to do is I'm going to let, okay, this is a different type of substitution. Notice what I'm going to do. I'm going to let the variable x be equal to sine of theta. I'm going to use theta as a different variable here. And we're going to do this for theta in this interval. Okay, going to x be sine of theta for theta between negative pi halves and pi halves. If you're thinking of the unit circle, right, then we're talking about between pi halves and negative pi halves, right, in terms of this internal angle going around the unit circle. We're talking about on the unit circle, right, the sine, of course, being the y coordinate. Sine is varying between -1 and +1 on that interval, right? So we'll come back to that in a minute. So notice the substitution is a little different. Usually when we do like a u substitution, I let the variable u, the other variable, be something like I might let u be 1 minus x squared. You can see where that's not going to work. If I let u be 1 minus x squared, what's under the radical, my du is negative 2x dx, and there's no x that's being multiplied anywhere in here, so I can't get the du out of this. I can get the square root of u, but I can't get the du. It's not going to work. And you can see the problems we have with this rather very simple looking function. And so trying to find the antiderivative of this is a problem. So notice the substitution is a little different in the sense that I said let x, the variable we have, be equal to some function of our other variable, in this case theta. Okay, so why does this work? Well, since x is sine of theta, then what is this square root of 1 minus x squared in terms of theta? Well, I replace x with sine theta and I get 1 minus sine squared theta. Right? Since x is sine theta, x squared is sine squared theta. But look at this, 1 minus sine squared theta. Since sine squared theta, I've got x here, but again you can replace x with theta. Sine squared theta plus cosine squared theta is 1. Sine squared theta is going to be what? 1 minus, or sorry, cosine squared theta is going to be what? 1 minus sine squared theta. So this right here is indeed cosine squared theta. And what is the square root of cosine squared theta? Well, it is cosine of theta. Okay, it is cosine of theta. Now, you might say, have a little question here. When you take the square root of cosine squared theta, we get actually the absolute value of cosine theta is what we actually get, because if indeed the cosine of theta were a negative number and I square a negative number, I get a positive. Square root is positive. It would still work, but we know we're only going to get the positive value to come out of this. And this is consistent now with this restriction on theta. Notice in x is the cosine of theta would be x, and the x coordinate is always positive over here. So this whole expression is now just cosine of theta. Now, we still have to deal with the dx. Since x is sine of theta, what is dx? What's the derivative of sine of theta? That is cosine of theta. So dx is cosine theta d theta. Dx is cosine theta d theta. And so all I'm going to do is change now to the variable theta, and look what happens. I have the integral. The square root of 1 minus x squared is just cosine theta. Right? And then the dx is what? Cosine theta d theta. So this is the dx, and this was the square root of 1 minus x squared. And cosine theta times cosine theta is cosine squared theta. And is this an integral we can do? Well, I hope so. I ask you guys to do this integral when we were doing the trig integrals. We actually derived the integral of sine squared theta, and then I asked you to do the integral of cosine squared theta. By the way, this is not sine squared theta or negative sine squared theta or anything crazy like that, right? The antiderivative of cosine squared theta, and this is from the textbook from the previous section on trig integrals. So we derived this formula for sine squared theta, and I asked you to derive this one. And there's two ways of writing this. The antiderivative of cosine squared x is 1/2 x plus 1/4 sine of 2x, or 1/2 x plus 1/2 sine of x cosine of x. And how are these related? Well, remember we have this double angle identity for sine. Sine of 2x is 2 sine of x cosine of x. That's one of our trig identities, right? So I've replaced sine of 2x with 2 sine x cosine x, and 2/4 is 1/2, and we get this over here. I'm actually going to use this second one in this case. Of course, I got theta here, so this will be 1/2 theta, theta over 2, 1/2 theta, plus 1/2 sine theta cosine theta, plus c. Okay. Now, one thing about trig substitution is, when we want to have what? The original variable for our answer. In other words, we want this in terms of x. This is in terms of theta. So how do I go about doing that? Well, we kind of already can see how we can do that, because I already know that sine of theta is just x. So this right here is just x. And cosine of theta I actually know now is what? The square root of 1 minus x squared. And what would theta be? What would theta be, though, in terms of x? Well, if x is sine of theta, so let me say if x is sine of theta, then theta is the inverse sine of x. And notice now really where this restriction here comes in, because we need that, right? When we go to the inverse sine, we have to restrict theta on this interval, and that's so that the sine function on that interval is 1 to 1. And so we have now theta is the inverse sine of x, because that's the relationship, right? If x is sine of theta, then theta is inverse sine or arc sine of x. Okay, and so that's going to be that value. Okay, and so what we get then is 1/2 the inverse sine of x plus 1/2 x times the square root of 1 minus x squared plus c. That's our antiderivative. Now, another way to get these, the Pythagorean identity gets us this relationship, but a nice way to sort of set this up too is to think about theta as being an angle and look at the corresponding triangle, the angle, acute angle in a right triangle. If you remember our definitions in terms of a right triangle of our trig function, so if I call this theta, right, x is sine of theta, or sine of theta is x over 1, right? So sine of theta is x over 1. And remember what sine of theta is in terms of this right triangle. We talk about what this side length being the hypotenuse. Side opposite the right angle is the hypotenuse. This side is the adjacent side to our angle theta. Again, this is theta. And this side is the opposite side to theta. So sine is what side over what side? Do you remember? Sine is opposite over hypotenuse. And x, or x over 1, opposite over hypotenuse, means we can write x as the opposite and 1 as the hypotenuse. In fact, think about this being on the unit circle, right? A radius of 1, right? That's what this point right here would be on that big unit circle. This unit circle that we drew over here. So what's this side length here? What is this value here? Let's call this a. Well, I think some of you already know the answer to that. By the Pythagorean theorem, I know that this side length squared plus this side length squared must equal 1 squared, which is 1, right? Sum of the squares of the two sides equals the square of the hypotenuse. And I can solve for a squared. It is 1 minus x squared. And so a is the square root of 1 minus x squared. And notice now I can use my other trig identity, ratio identities. In other words, sine is opposite over hypotenuse. Cosine is what? Adjacent over hypotenuse. So that's a over 1. A cosine of theta is just a. Cosine of theta is the square root of 1 minus x squared, which is what we already knew. But I can also get things like tangent. What would tangent theta be? You remember what tangent is? Tangent is opposite over adjacent. So tangent theta would be x over the square root of 1 minus x squared. And so on. You can actually get secant, cosecant, and cotangent all from this. So this right triangle is very helpful with doing our trig substitution. Okay, so in general then, how do we deal with integrals involving the form a squared minus x squared? This is the first form we're looking at. Here again, a is 1. Here is the general technique. Right? If that occurs, we're going to try x equal a sine theta. Now, in the previous case, a was just 1, so we used x equals sine theta, right? With theta again in this interval, notice that dx is going to be a cosine theta d theta, and the square root of a squared minus x squared. If I replace x with a sine squared, or a sine theta, I get a squared sine squared theta. Factor out that a squared. It comes out of the square root as just a. I'm left with 1 minus sine squared, that is cosine squared. Square root of cosine squared is cosine theta. And so we get that. You can also, again, draw that right triangle to get that relationship, right? If I draw that right triangle with this being theta, and x is a sine theta, that means, of course, that sine theta is x divided by a, right? If I divide both sides of this by a, and so sine theta is opposite, x is opposite over a hypotenuse, which is a. And then if I use the Pythagorean theorem, I'll let you show that this is indeed the square root of a squared minus x squared. All right, and so you get cosine theta is a squared minus x squared over a, or a squared minus x squared square root is a cosine theta. Okay, so with that, let's look at this integral down here. Notice this integral doesn't have just the square root, but I have 4 minus x squared to the 3/2 power. So there is a square root in here, right? It's the square root and then cubing it. So in the same, and it doesn't matter what power we have here, we can express it as a power of 1/2. A lot. If we could do that, then we're going to be dealing with these type of integral the substitution technique. All right, so here I've got 4 minus x squared, and so notice the value of a is 2, and so I'm going to use x equal a sine theta, x equal 2 sine theta, and I'll immediately say my dx, which we need to include, is 2 cosine theta d theta. Okay. Now I'll go ahead and draw my I can go ahead and draw my right triangle right now. And notice that I have sine theta is what? X equals 2 sine theta. So sine theta is x divided by 2. Opposite, right? Remember, opposite over hypotenuse. Opposite over hypotenuse. So x is the opposite, hypotenuse is 2. And if I solve for a here, again, if I call this a, of course, a squared plus x squared is 2 squared, or 4, and I get a squared is 4 minus x squared, or a is the square root of 4 minus x squared. Okay. Now, so we could use this, and we sometimes will use this later on when we get to convert back from theta to x. What I want to look at now is a couple things. I've got x squared up top, so I know what x squared is. X squared is going to be what? Since x is 2 sine theta, x squared is 4 sine squared theta. Okay. What about the 4 minus x squared to the 3/2? So I've got the dx covered. I've got x squared covered. What about the denominator here? Well, that's going to be 4 minus 4 sine squared theta, all to the 3/2. All right. And notice I can factor out a 4 from here, leaving 1 minus sine squared theta. This is all still to the 3/2 power. Remember, this is all inside the 3/2 power. And then this 1 minus sine squared theta we know is what? By the Pythagorean identity, that's cosine squared theta. Okay. So I got 4 cosine squared theta. Now to the 3/2 power, what's that? That is what? The square root for cosine squared theta cubed. And what happens when I take the square root of 4 cosine squared theta? I get 2 cosine theta, don't I? And then cube 2 cosine theta, I get 2 cubed, which is 8 cosine cubed theta. So I've used the Pythagorean identity in that, right? The fact that cosine squared theta plus sine squared theta is 1, and so 1 minus sine squared theta is cosine squared theta. And so now everything's in terms of theta, and so we're going to rewrite this, and let's do that. Up top I've got x squared, which is 4 sine squared theta, times dx, and what is dx? 2 cosine theta d theta, all over 4 minus x squared to the 3/2 power, which is what? 8 cosine cubed theta. Could do a little simplifying here. 4 times 2 is 8 divided by 8. So do you notice these all become 1. And I got cosine theta here, and cosine cubed, I can do cosine squared, right? Divide top and bottom by cosine theta. And what I'm left with is the integral of sine squared theta up top over cosine squared theta, d theta. Pull that d theta out. Okay, so we've simplified that. So what's this going to be? Well, this, if how can we do this? Notice sine squared theta divided by cosine squared theta is just tangent squared theta, right? Sine divided by cosine is tangent squared theta. Now, what's the antiderivative of tangent squared theta? Well, I don't know off the top of my head. We know the antiderivative of tangent theta. We've derived that from basic substitution by rewriting tangent as sine over cosine. It doesn't work. Substitution doesn't work here because if I let u be cosine squared theta, du is going to be 2 cosine theta sine theta d theta, and I don't have that up here on the top. I just have sine squared theta. So substitution doesn't work. However, think about the Pythagorean identity. We use the sine squared theta and cosine squared theta 1. Right? Sine squared theta plus cosine squared theta is 1. Here, tangent squared theta plus 1 is secant squared theta. So notice if I subtract 1, tangent squared x is what? Secant squared x minus 1. That'll be an important relationship. So I'm going to replace tangent squared theta with secant squared theta minus 1. And you say, well, what does that get us? We're now from a tangent squared theta to a secant squared theta. However, whereas I don't know, sorry, there's a d theta here. When I don't know what the antiderivative of tangent squared theta is, I do know what the antiderivative of secant squared theta is. And you should as well. What's the antiderivative of secant squared theta? That is tangent theta. Right? We know the derivative of tangent theta is secant squared theta, so the antiderivative of secant squared theta is tangent theta. Antiderivative of 1 is theta. So that's how we can get our antiderivative. Now, the question is, what is tangent theta and what is theta in terms of our original variable? Well, let's go up here. So first of all, right, since sine of theta is x over 2, I know that theta is the inverse sine of x over 2. And I have my right triangle. I know a is equal to this. So what is tangent theta? Which is down here in our antiderivative. Tangent theta is what? Opposite over adjacent. Opposite over adjacent. The opposite side is x. The adjacent side is a, which is this thing. All right, so the opposite over the adjacent. Okay, so this thing here, and of course this thing here, we're going to grab both of those things and we're going to bring them down. And replace them with, use them to rewrite these things. So we said tangent theta is x divided by the square root of 4 minus x squared. And theta was the inverse sine of x over 2. Okay. And that's the antiderivative of the function. So, really complicated process it seems like in some ways. But it's very nice. It allows us to do something what we can't do. We don't know what the antiderivative is here. Again, if you try and use a regular substitution, it's not going to work out. If you let u be 4 minus x squared, du is going to be 2x, negative 2x dx, and you only got an x squared dx. Okay, it's not going to work out quite right. But this trig substitution works for us. Okay. Now, sometimes with trig substitution, the integral you get here after you do the substitution can be quite complicated. This one was a little tricky, right? Recognizing that this was tangent squared theta was important, and then recognizing that I can use that Pythagorean identity to rewrite this into a form that I do know the antiderivative of these two things. So in general, a lot of times you can get some messy ones, and in the book sometimes they'll say you can use, this is from the previous section on trig integrals. This is a table of integrals involving the trig functions, and of course we use this one. We looked at these power reducing integral forms for powers of sine and cosine, but we have other formulas that we can use as well. Some of the things we already know, but this list could come in handy. So if you get stumped on some, we might use this list to help us out again for convenience. Okay. All right. Let's take a look at another problem then. Actually, we'll stop this video and we'll look at another problem involving this method. One thing to note, we are using x equal a sine theta. You could similarly do the substitution with x equal a cosine theta because of the relationship between sine and cosine and that Pythagorean identity. We just usually choose sine theta because the dx is positive, right? The dx is positive cosine theta. If I choose x to be 2 cosine theta, then the dx is going to be negative 2 sine theta d theta. Just to get rid of that negative sign is one reason not to do that sort of substitution. Okay, so we'll take a break and then we will do some more examples in the next video.